right, so then let's see how to construct such a signature scheme. And RSA is a very famous one that's widely used even today. So RSA signature, Rivest, Shamir, and Adelman. And so the way it works is the following. By the way, RSA can also be used for public key encryption, but it's just think about it in terms of signature so that it doesn't get confused. And yeah. So for keygen, what is going to happen is that we're going to pick two random primes. P and Q of 2048 bits. So, and then, there's a technicality that are both 2 modulo 3. Anyways, it's a technicality for reasons I'll mention later. But basically, they have to be of this size because, at least today, factoring a number that consists of primes of this size is going to be difficult. And we'll see that the RSA signature relies on the difficulty of factoring. Okay, then we're going to have n is equal to p times q. Okay? So this is going to be the public key. The public key is going to be this n. Now, let's see how to derive the secret key. So there's a function called phi of n, or called Euler's totient function. And this was taught in CS160, but also we have a quick reminder of this in the notes. But basically, this function is the number of elements, the number of numbers that are coprime with n. Okay, so it gives you the number of integers 0 that are coprime with n, namely the GCD of that number and n equals 1. And in particular, from CS70, phi n is equal to P1 times Q1. And this is going to be the order of the group modulo n. Okay, so basically what do I mean by this? For all values a, if I take a to the value of phi of n, I get 1 modulo n. And you can kind of see this, that let's say that if n were to be a prime, p, then, so it wouldn't have the q factor, then phi of n would be p minus 1. So you have that a to the power of p minus 1 is 1. That's that's Fermat's little theorem. Okay? And this is just basically Fermat's little theorem extended for a number n that's composite of p times q. Okay? So then you want to compute d such that 3d is equal to 1 modulo phi of n. Okay, so you can easily do this because if you know phi of n, which you know based on the p and the q, then you can easily compute this d. And now the secret key will be this d. So this is the secret key, and this is the public key. In particular, P and Q are secret. P and Q are not to be disclosed by the key generation algorithm. The key generation algorithm is just going to reveal n as part of the public key, and this is the thing that the adversary will also see. Everyone gets to see the n, but no one other than the signer gets to see P, Q, or D. In fact, you just want to toss away P and Q and then just keep D around as your secret key. Any question? Okay, so this was literally just the key generation part, which is the most complicated part of the algorithm. So this was key generation. So now we're going to see how we sign and how we verify. All right, so to sign, remember that you sign with the secret key, which is D, a message. What you do is you take the hash of the message M, you raise it to the power of D, modulo N. This is the signature. Now, to verify, you need to be able to verify with the public key, which is your N, the message M and some signature. What you do is you simply take sig to the power of 3, modulo N, and you check whether this is equal to the hash of the message modulo N. Okay? So the first thing we want to check is correctness. I want to check that if I verify a properly signed signature, I get, I get the correct verification. So let's check correctness. First, can someone see why this is correct? So basically, we're taking the signature to the power of 3 and checking if it's equal to the hash of the message. This, I should have said the same. It's the same. Exactly. So let's work that out slowly. Okay, so let's take the signature and raise it to the power of 3 and see what happens. So you have the hash of the message M, D, to the power of 3, everything modulo N. Again, modulo N's, you can take them out of the parentheses always, because it's basically you're working within the modulo N group. So this is just hash of the message to the 3D times modulo N. Now, let's take a look here. We know that 3D is 1 modulo phi of N. What this means is that there exists some integer, I'm going to call it R, such that 3D is equal to R times phi of N plus 1. Okay, so now I'm going to plug in this value for 3D. So I'm going to get hash of M, the power of R times phi of N, plus 1 modulo N. All right, but I also know that I'm just going to rewrite this as hash of M to the power of phi of N, everything to the power of R, times hash of M, modulo N. All right, but I also know that anything to the power of phi of N modulo N gives me 1. So this whole term is going to be 1. So I'm going to be left with just hash of M modulo N. Any question on this? Is it clear why basically this will verify, because this will be indeed equal to the hash of the message. So this is the correct signature scheme.